Hey guys, it's me and I'm going to show you how to solve this normal stress problem. Now, before we proceed, let's analyze the question. It says that we need to determine the average normal stress at points D and E, meaning we need to find the stress at each point D and point E. And then we need to represent those stress on a volume element located at each of these points, meaning we would just need to draw a volume element, for example, a cube. And then identify what the stress is in relation to the forces outside, whether if it's a compressive force or a tensile force. Let's begin. First, what are the givens? For the pipe, we are given the values of a inner diameter of 20 millimeters and then an outside diameter of 28 millimeters. With the rod, we are given a diameter of 12 millimeters. Now, how do we solve for the stress? Our formula for the stress is just a force over A. A, which is area. Now, we do have the forces, which is the kilonewtons in the figure given, but we don't have the area. But what we do have are the diameters, meaning we can get the area of a circle in terms of its diameter. How do we get the area of a circle in terms of its diameter? We know that for solving for the area of a circle, we use the formula pi r squared. And we know that radius is just d over 2 squared. If we simplify, we'll get d over 4 squared. We cross multiply, that'll give us pi over 4 d squared. This is how we solve for the area of a circle in terms of its diameter. Now, we can see that there's two diameters given, which is the inside diameter and the outside diameter when it comes to the pipe. So what that means is that this pipe is actually a hollowed pipe. This is the outside diameter, skin, which is 28 millimeters, and this is the inside diameter, which is 20 millimeters. To get this shaded part, which is the area, we just need to subtract both diameters. Let's start with the pipe. Pi or multiplied by the outside diameter subtracted by the inside diameter. Oops. Which gives us an area of 301.59,289 millimeter squared. Why millimeters squared? Because if you multiply a unit by itself, it becomes twice of itself. Now let's proceed to finding the area of a rod, of the rod, which is just pi over 4, 144. Well, I mean, 12 millimeters squared. That's just 144. Pi 4, 144. That'll give us an area of 113.09734 millimeters squared. Now that we finally found the areas, we also have the P. We can finally solve for the stress of each. Before we proceed, let's look at figure. We can see that there are many forces, outside forces. There's 6 kilonewtons, there's 8 kilonewtons, and there is 4 kilonewtons. How do we know which to use and which not to use for each points? Well, we can simplify it by just cutting the pipe so we can only focus on 4 kilonewtons. Basically, it'll end up looking like this. Four kilonewtons, 4 kilonewtons, because of equilibrium. Since we cut it too, but so you won't get confused, we don't need to write that, or at least I don't need to write it down. So we have 4 kilonewtons, and since we are dealing with millimeters, I want to simplify it and convert kilonewtons into newtons. That way, we'll end up with megapascals. You'll see. So we have 4,000 newtons because 1 kilonewton equates to 1,000 newtons. So we have 4,000 newtons over 301.59289 millimeters squared. That'll give us 13.26 Newton millimeters squared, or 13.26 megapascals, because Newton millimeter squared is just megapascals. That's why I decided to convert 4 kilonewtons into 4,000 newtons. Now let's head on to to the rod. The stress of the rod at point E. We'll just substitute the values. 8,000 newtons over 113.0973 millimeters squared. That'll give us 70.74 megapascals. We've now solved for the stresses of each point D and point E. Now we need to determine what the stress represents in relation to the outside forces. So we know that at point D, can see that it goes to the right, meaning it's a compression. It's experiencing a compressive force. Because if we apply the logic of equilibrium, if this is going to the right, then the other force should be going to the left, or must be going to the left. That's why it's being compressed at point D. Now at point E, let's imagine a volume, let's say cube. It's actually a tensile force. Because since the original force is pulling away at point D, i.e., then with the law of equilibrium, this must also be pulling away from point E, meaning it's being stretched out, so it's a tensile force, while this one is a compressive force. Well, there you go. We've answered it.